In this third video we're going to try and explain Einstein's photoelectric equation. We know from previous video that the energy of the incoming photons, the photons of light, is proportional to frequency, E equals hf. So the energy the photon has depends on only its frequency. Okay, it doesn't depend on the intensity, anything like that, just the frequency. And Einstein went on to use this model for light to explain the photoelectric effect, and in fact he won the Nobel Prize in 1905 for doing so. So what did he say? Well, what Einstein said was that the energy that comes in from the photon is used to possibly do two things depending on how much it is. Some of that energy, when it's absorbed by the electron, is used to get the electron out of the metal, and the energy that's needed to do that he called the work function. It's represented by this Greek letter here, phi. Greek letter phi represents the work function, and that's the minimum energy needed to get the electron out of the metal. If the photon that comes in, the energy here, h times f of the incoming photon, is greater than phi, so it's greater than the minimum energy needed, then not only is the electron going to come away, but it's going to come away with extra kinetic energy. Okay, so the energy of the photon, some of it is used to get the electron out of the metal, the work function. Some of it is extra, if there's any left, is extra kinetic energy of the emitted electron. So Einstein made a few assumptions here. He said that all the energy of the photon must be absorbed by one electron in one go. Okay, it can't take in a little bit of energy and then a little bit more from the next photon, a little bit more, and so on. It's all or nothing. It either receives all the energy or none at all. So this equation, Einstein's photoelectric equation, is really just a conservation of energy equation. Every term in the equation is an energy. Hf is the energy of the photon. Phi, the work function, is the energy needed to get the electron out, and of course Ek is just the kinetic energy of the emitted electron. Strictly speaking, it's the maximum kinetic energy, because some electrons will be embedded deeper in the metal and they might come off with lower kinetic energy, so you should get used to using the term there for Ek for the maximum kinetic energy of the emitted electrons. Now, we know when we did the experiment that there appeared to be a frequency that worked, in our case ultraviolet, and a frequency that didn't work, visible. So there must be some point, some cut-off point, where there is a sort of threshold frequency, a minimum frequency that causes that effect to happen. Okay, so for the zinc it's somewhere between visible and ultraviolet, somewhere in that region, and of course there's an energy associated with that frequency, hf. Now if that's the minimum energy, if that's the minimum energy that will cause the effect to happen, that's obviously going to correspond to the minimum energy needed to get the electron from the metal, which we defined earlier as the work function. So the work function, phi, is going to be h multiplied by this value here, the threshold frequency. Okay, so that's an important little relationship, crops up in exams quite a lot. That's not a very good cue, is it? Crops up in exams quite a lot. You might be given the work function and asked to find the minimum frequency at which the effect happens, or conversely given the minimum frequency at which the effect happens and asked to find the work function, and then put either of those back into Einstein's equation. Alright, so this little relationship here, together with Einstein's photoelectric equation, will probably be enough for you to solve all numerical photoelectric effect calculations. And just to finish with two important things about the light in the photoelectric effect, and things you could change about it. The first thing obviously you can change about the light is how bright it is. Okay, now in physics, brightness, the better word for brightness is intensity. You'll meet it again later, but for the moment just think of intensity as meaning brightness. If we have brighter light, all that means is that there are more photons. We haven't made the photons more energetic, there are just more of them, and that makes the light brighter, more intense. The total energy arriving will be greater. But because there are more photons, all that means in terms of the photoelectric effect is that we will get more electrons coming off. We're not going to get more energetic electrons. They're not receiving any more energy. The energy of the photons is exactly the same as it was before. So increased brightness means more electrons coming away. The other thing we can change about the light, of course, is the frequency. If I change the frequency of light, so for example if I go from red to UV, what I've done is change the energy of the photons. And if I change the energy of the photons, if I've got more energy coming in, the electrons are going to receive more energy, so they're going to have a greater kinetic energy when they're emitted, a greater maximum kinetic energy when they're emitted. Remember, each electron absorbs all the energy from one photon, so if I increase the frequency, the energy of the emitted electrons goes up. If I increase the brightness, then the number of emitted electrons goes up.